Hola, Diego. Forgive me being late. One of my laptops is giving trouble. How are you doing today?
Hello, Cassie, and good morning. Doing great.
Okay.
We are just
Alrighty.
going to begin.
Great, perfect. Okay, so I may just switch laptops in between, but I'm here. I have to step out of between 14 UTC and 16 UTC, but I'm still
Okay.
going and still watching the recordings.
No problem.
Thank you, Diego.
Thank you very much. Good morning. Good morning, everyone, and welcome to the 5th day of the GNC-A Americas Caribbean Training Workshop. And before we begin, just remember to have your Colab notebooks ready for the homework reflection. And please run the first cold cell now. And your notebooks will be ready when we start. We are approaching the end of the training, and the idea for this last couple of days is to understand additional details about the GNC-A system and also the system community. We will explore more products that are available in the broadcast that are not only ABI and GLM and NWP, okay? So we are going to explore other data sets. And now that we know the basics of Python, we will learn some new tricks, okay? That will greatly help in creating our scripts and creating value-added products to our Met services, okay? And on the 4th day, we have learned how to create the split water vapor and the split ozone channel differences. And we have seen that they are components of other RGBs. Then we have seen details of the GNC-A ingestion software called the Fast Professional Client, which receives and manages the files that are uploaded by the data providers. We also have seen some maintenance aspects that we need to check periodically. And what to do if our station stops receiving data for some reason. And to facilitate things, we have seen a maintenance flowchart with all the steps. And today we will also access the station from Granada, check the fast client and some parameters requested in the maintenance checklist assignment available in Moodle. Okay, just let me check if I have, and here it is. I will access it later. Okay, and this is the Proteus interface processing the data set, and here you have the Showcast software processing data set as well, right? So we are going to explore the station today that I have the credentials. And in the 4th day, in the Python hands-on, we had the second part of the NWP data processing examples. And we have learned how to create our contour plots, create custom color tables, create animations, plot streamlines, wind vectors, bars, and we have also seen that it's possible to calculate complex information, okay? And today, we will begin with the homework reflection and learn how to create the dust, the ash, and the SO2 RGBs. And these are very nice. And after that, now that we know our ground station in details, we know every component, the antenna, the feed, the filter, the LNB, the receiver, the fast client, and the workstations, right? Now we are going to check other aspects of the system. And today we will learn that you may become a data provider. And we will try to make some test uploads to the system. So you see a file that is in my laptop. It will go from my laptop to Georgia, to the antenna at Georgia, to the satellite, be rebroadcast to the system and be received by our ground stations. Okay, so we will try to do that. And in the Python hands-on, now that we know the basics of Python and that we have seen the possibilities, we may start learning some tricks that will greatly facilitate the development of new scripts and products. And we will also review how to create advanced plots and animations, right? And also, If you have the time today, we will repeat what we have done during the first day and explore the content of the system using Panoply, but also using Python. So we will start exploring more products that are not GLM, ABI, or NWP. So we will check and explore the sea surface temperatures, anomalies, total precipitable water, vegetation, ocean color, and much more. Okay, so we'll have some fun. Also, I would like to remember that recordings from the previous 4 days are available in Moodle. And it's the last link here, 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 and here. It's the last link in the end of each day. And you just need to click at the link and insert the password. And there is a password for each day. And if you watch the recordings to review the presentations and do not understand some of the concepts or procedures or any part of the hands-on activities, you may send me a message on Moodle by clicking at this icon here. Or you may send me an email and I will try to help, right? For example, one of the participants of the training, Wayne from CIMH, is trying to create a specific plot, right? He wants to create an image of the true color RGB during the day, and during the night, he wants to plot the city night lights from VIIRS and the 10.3 micron band enhanced with a color map. And also he wants to have a smooth transition between the day and the night regions. So since the beginning of the training, we start exchanging some emails, right? And I sent him some script examples and some blog posts with the information he wanted. For example, right, just before we began, just for you to understand the objective of this training, one of the objectives of this training, I shared with him this page here, which is a GitHub example with the true color script, right? And I mentioned that he need to calculate the zenith angles, the sun zenith angles, right? Then apply the sun zenith corrections, then apply the Rayleigh correction, calculate the recipe, and apply what is called the Sierra stretch, right? And also I have shared some links with Wayne. First, this one. Because he wants to make a transition between day and night, right? And I mentioned that he needed to first calculate the sun zenith angles, right? And with the sun zenith angle calculated, all the pixels with the zenith angle of 85 degrees is night. You need to plot an image. Now the pixels with a zenith angle below approximately 85 degrees is day. And in your code, you will know how to plot the other composite, in this case, the true color, as you're seeing here. This is just an example for Brazil, right? As you may see here, the transition is abrupt. It's not smooth. Here, here, and here, okay? So I have shared another link with him here. So he understands how he can make a smooth transition between day and night, like in this example, right? And in this example, we need to apply a transparency gradient between this point and this point. And this is also based in the solar zenith angle between 75 degrees, more or less, and 85 degrees, more or less, right? And in the end, you have a beautiful plot like this one, right? And you also may plot, as you see here, let me open it here, open a new tab. You can plot the VIIRS night lights, as you are seeing here, as a layer, okay? And you have all this information, the digital files available in your GeoMetCast America's ground station, so you can manipulate the way you want, okay? And also you can use the libraries. We have mentioned that throughout the course to make these calculations. For example, to calculate the sun zenith angle, you may use the pi orbital library. okay? And thankfully, right, let me show you, Wayne is almost there. Let me just minimize my slides. And this is a plot developed by Wayne. Thank you for sharing, Wayne. And as you may see, he's plotting here the true color during the day and the enhanced 10.3 micron band during the night with a smooth transition between night and day, right? However, in this example, he still needs to make some corrections because the enhanced clouds here, right, are also being plotted during the day over the true color RGB. And he doesn't want to do that, right? So he will make some adjustments, or he is making some adjustments. And during the night, for some reason in his code, the night lights, as you see here, they are not in the right position. You have some night lights in the ocean. So but this will be easy to correct. And I sent him some suggestions this morning that you can change the order of the layers, changing a parameter in the script called the Z order, okay? And he would be able to plot the true color over the enhanced clouds. And this morning he sent me an update, this one. And as you see here, he has the true color during the day, a smooth transition here, and the enhanced 0.3 micron band enhanced during the night, right? And now he just need to correct the position of the night lights, okay? So this is the kind of thing, and I'm very happy that Wayne was able to create this, right? And he was also able to add custom information in the plot like logo, CIMH's logo, right? And a title here inside the plot, as we are going to see today. Okay, Go 16 true color RGB, the day and the time. All right. So this is what I would like you to try and to motivate you. Create custom information faster than the images that are available in the internet and with value added information that it's not available anywhere. Okay. So if you have any comments or questions when you try to create your own plots and products and are having difficulties, even after this training, you may send me an email and I'll be happy to help you when I can. Okay, and let me return to my PowerPoint. Oops. Just an additional comment. When we finish the session today, please leave the Zoom meeting. Okay, otherwise the system will keep the recording until the last participant leaves the room. And that's not good because it increases the recording file size and the duration without content, okay? And the file uploaded into Moodle will be much larger, much bigger, okay? And talking about Moodle, you may download and access all the resources we will see today under day number 5. Here, day number 5, okay? Now let's begin our homework reflection and learn how to create the dust, gash, and the SO2 RGBs. So I suggest you have your homework notebooks ready, right? And today we will begin with reviewing assignment number 5, dust RGB, okay? This is the recipe of the dust RGB. And as you see here in the table, we need 4 channels to create this RGB. The 12.3 micron band, or channel 15, the 10.3 micron band, or channel 13, the 11.2 micron band, or channel 14, and the 8.4 micron band, or channel 11. And that's the first information we need to know, right? And now let's copy the script from the Hermes example number 2 in this homework notebook. and paste it in our code cell. So we don't need to start from 0. Okay, so I'm going to script number 1, example number 2, the air mass recipe. I will copy it, right? And paste it under assignment number 5, this one. Okay, if I run this code cell the way it is right now, I'm going to see the air mass RGB, but I don't want the air mass RGB, I want the dust RGB, right? And first I will change here the comment section. Instead of air mass, I'm going to add dust RGB, okay? Then I will select date here. Using the same variables we have seen in the 3 examples, using the same techniques we have seen in the split window difference, the night fog difference, split water vapor, split cloud phase, and split ozone. So the same variables. And for the date, in this case, I'm going to add 2020, June 18, 17 UTC. Okay. And now I'm going to change the download function calls, right? With the bands I need. Download CMI instructions, right? And I need bands 15, right? And that's in the recipe. And if you do not know the band numbers based on the wavelengths, you may click here at the reference table, okay? And check the band numbers. Band number 15, band number 13, band number 14, and band number 11, okay? And if we look at our table, we will see that we have the same resolutions for all these bands. Band 15, 2 kilometers. Band 13, 2 kilometers. Band 14, 2 kilometers. And band 11, 2 kilometers. Okay. And because of that, let me return here. And because of that, we don't need to do any tricks to match the dimensions, as we have done in example number 3, the cloud phasing station. Okay. And here I'm just reading each band every 4 pixels as we have learned, because I want to make the processing faster, and that's it. But you could read it every pixel. And here I calculate my recipe. I will calculate the R for red, G for green, and B for blue, each component according to the recipe. Okay. So the red composite is band number 15 minus band 13. And here I have called it data 1, but let me change it. Data underscore CH15. And on data 2, I will have data underscore 30. And on my third date, I will have data channel 14. And on my data number 4, I will have channel 11. I have just changed the name of my variables to make it easier to understand throughout the script what we are doing. Okay, so I have read the 4 bands, and now I'm going to apply the calculations according to the recipe. Okay, so in this recipe, we have data 15 minus data 13 as the red component. Sorry. Oh yeah, channel band 13. In the green component, I have band 14 minus band 11. All right. And my blue component, according to the recipe, is band 13 alone. Okay. Band 13 alone. And then I have the minimums and the maximums. And if you see here, let me open the quick guide. This is the quick guide for the dust RGB, right? I have For the red component, between minus 6.7 and 2.6. For the green component, between minus 0.5 and 20. And for the B component, we have minus 11.95 to 55. Okay, now let's add these thresholds here. For the R component, minus 6.7 to 2.6. For the green component, minus 0.5 to 20. And for the blue component, minus 11.95 to 15.55. Okay. And now that we have the values, in our next instruction,
-0.5. You put 0.5.
okay. In the next instructions, right, we will use the numpy clip function that will make everything that is lower than the minimum, it will keep the minimum, and everything that is greater than the maximum, it will keep as the maximum. Okay. And this is the same in the example from the second day or the third day, I can't remember. We did this. R, everything that is smaller than R min, we will keep as the R min. Okay. And this clip function and everything that is greater than the R max will keep as the R max. Okay. So with this clip function from numpy, we are doing the same, but in a single line. Okay. So I don't need this. I'm just have less lines of code and doing the same thing. And I have a comment. Cassia, minus 0.5 in the green component, correct? All right, minus 0.5, not positive. Thank you very much, Cassia. And in our next step, we need to configure the gammas. And if you look at the table for the first time, in these examples, we have a gamma different than 1 for the green component, right? We have 2.5 instead of 1, right? So we need to insert here 2.5 as the gamma. And remember we mentioned in the second day that the gamma correction is used to change the contrast, okay? So here we are changing the contrast of the green component by a factor of 2.5, right? For green, minus 0.5 to 20 degrees. All right, thank you very much. 2.5 to 20 degrees. Thanks again, Rain. Great. All right, and in our next step, we will, I'm happy that you are understanding this, right? Excellent, thank you very much. And in our next instruction, we need to normalize the data between zeros and ones as required by Python to create an RGB, right? Also, we apply the gamma correction with the result to the power of 1 over gamma, right? And in the first line, gamma will have no effect. In the blue component, the gamma will have no effect, but in the green component, the gamma will have a big effect, okay? Also, if you look at the table, and this is we have used the script from the ARMAS RGB. If we look at the table, we do not have any inversion. Blue channel is not inverted. If we look at the ARMAS RGB here, the blue channel is inverted. But in our assignment number 5, it is not inverted. So I just need to delete this instruction here. I don't need it or comment, but I will delete it, right? And finally, we create a stack using the same command from the ARMAS RGB, the numpy stack, right? And I'm running the code cell now, so I can check if we will have the right RGB calculated, right? So with the stack function, we create this combination of the R, G, and B components, just like as we have done with the R mass and the day cloud phase distinction. Okay. Oh, and I will also change the title to dust RGB, right? And I will change the image name to image dust. Okay. And run the script. And this is what we have. I have the wrong name here because I have run the code cell before the change, but there's no problem. And here we have the dust RGB. And this is for the same date of the example number 1. The split window difference. You see the huge dust plume here? And that's the result for the dust RGB here. And if we open the quick guide, let me close some tabs here. If we open the quick guide, you see the dust plumes are easily distinguished from the surrounding clouds, right? And dust appears as tones of magenta, right? Let me open Paint and let's play a little bit. Here, this is the RGB edition at Paint, right? And you see magenta here, right? Is when we have a large contribution from red and a smaller some contribution from blue and a very small or no contribution from green, right? And if you look at the recipe here, large contributions from red, right? The split window difference, right? The split window difference, large contributions from red means thick clouds or dust, okay? And a large contribution from blue indicate warm surfaces. And when you combine a large contribution from red and a large contribution from blue, as we have seen in Paint, we have the tones of magenta. And if we go to the second page of the quick guide, you see the interpretation for every color range in this RGB. For example, magenta, dust plume, right? Light purple, low water clouds. Here, too. Here, right? And shades here for mid-thick clouds. And black, high thin clouds, as we can see in our Colab notebook, right? And shades, right? Here, mid-thick clouds. Black, high thin clouds here. Okay, so this is our dust RGB, right? And for the ash RGB, right, we have a very similar RGB called the ash. And if we search for the quick guide at the Ranby webpage, Ranby, and we search for the ash RGB here. Let me send you the link through the chat box. You'll see that it is very similar and that it uses the same recipe, the same channels, same channel differences, but they have changed the minimums and the maximums for each component, right? This is not on the homework, this is not an assignment, but let's try to create it now, right? And because it is very similar, I will just copy my script, use it to create the dust RGB, and I can copy it. Let me delete this. I can click here, copy cell. Again, 3 points, copy cell, and I will paste it. right? I have just pasted below the dust, and I will create the ash RGB, right? I will change the title at the comment section, and I will change the minimums and the maximums according to the recipe, okay? Sorry. So we have the same bands, right? But I will change the minimums and maximums. So between minus 6.7 and 2.6, minus 6.7 and 2.6, right? The green, minus 6 to 6.3, minus 6 to 6.3, positive. And for some reason, they have the recipe in kelvins, right? And let's just convert to C. So we have between minus 29.55, minus 29.55, and oops. 29.25, 29.25, okay. And for the gammas, we do not have any gammas above 1. So I will change here to 1, right? Let's change the title to ash here, ash RGB, and insert a date with an ash bloom. And I'm also going to change the name to ash. Let me change the date, and I'm going to add a date here, 2019, July 19, 12 UTC, right? And that's the date for the Ubinas eruption, as we have seen in the third day. And I'm going to send you this instruction in the chat. Let me run the script again, right? It is downloading the files, right? Let's see the results. And this is the result. This is the ash RGB, right? However, if you look here, Ubinas volcano is in the southern Peru, and you have an eruption here, but you can't really see it, right? Because it's very small. And unfortunately, in Google Colab, you cannot zoom in, right? But you can zoom in if you run the script locally. Oh, another comment is that we have a script in the Colab notebook from the first couple of days where you learn how to plot specific regions, right? And crop your image. But now let me try to run this script locally so I can make a zoom in an interactive window. So what I'm going to do, right? And I'm going to do now, just a moment. I'm going to access my folder where I have my script, which is VLab Python goes. I'm going to copy script number 1 and paste and change the name of this script to script ash. Okay, script ash, and I will open it in my local editor, which is Notepad++ in this case, right? So here I have the script, but I have copied script number 1. What I'm going to do is I'm going to copy the script from my Colab notebook and paste it in my local machine. as this, right? But I'm going to make some changes. In the local machine, I do not have the content folder, but I have a samples folder if you follow the procedures available in the complementary activities, right? So I'm going to do this, right? Change the folders. And I'm not going to read every 4. I'm going to read every 1 because I want to give a zoom in the maximum resolution to that region where we have the eruption. And I'm also going to change the folder where I have my shapefile. And in my local machine, if you look here, I have the shapefiles. Let me run this script because it takes a while, okay? Just a moment. You open on the prompt, and you have all these steps available in Moodle, right? I'm going to activate my Conda environment, Conda activate workshop. And I'm going to my working folder, cd c column slash vlab slash python slash goals. Let me just save the script, right? And run it with python script ash. And if I do not have any errors, here you see downloading file number 1, then 15, downloading file number 2, 13. I have an error. Let me see which error is this. Oh, here's an important thing. Look that I have forgotten to change to read band number 11 every 1. I was reading every 4. And that is why Python says, hey, I could not make an operation between data with different shapes, right? That is why I need to read all the files with the same shape. Let me run it again. Downloading band 1, downloading band 2, sorry, band 15, band 13, band 14, and band 11, okay? Let's wait a little bit. It takes a while. And here, just for your information, I have a 16 gigabyte RAM notebook, and it is a i5, right? It is processing, and we should have the interactive window appearing soon. And here it is, here. And when I'm running scripts locally, I can zoom in and out. Now let's click here at the magnifier and zoom in the region you have the eruption. And here you have it. We are plotting an image with the maximum resolution, okay? Here you have the ash plume from the Ubina's volcanic eruption. And if we open the ash quick guide here, you see that red magentas, right, is pure ash, okay? Bright greens are sulfur dioxide gas, or SO2. And yellows, ash mixed with SO2. And that's what we are seeing here, right? Reds to magenta, bright greens, and yellows. So we can differentiate, right? Reds to magenta, pure ash, right? Bright greens, SO2. Yellow, a mix of both, because when you mix green and red, you have these tones here, okay? And this differentiation is possible using the RGB techniques, right? Now let's see another eruption. And now from Cumbre Vieja, let me close this. Now from Cumbre Vieja in the Canary Islands in October 9, 2021. So I'm going to change this date here to 2021 and 09 1330. And let me just run my script locally as well, because as you have seen, it takes a while. I'm going to run it locally and in Colab. Okay, 2021 and October 9, 1330. Okay, let me run it. And let's see the result. Downloading the files. Downloading the files. I'm running at the same time in Colab and locally, right? And that's the idea of the training. You have both options. But when you are developing products for your med services, you need to run locally, right? Processing. And when we are processing products in Colab, you are using the virtual machine from Google, provided by Google. And when you are running the script locally, you are running in your own machine. So you are using your resources. And that's why we are not processing, for example, band number 2 in any one of these examples, because it is a half-kilometer band and the full disk is huge and it could load our computers, right? So here you have the result, but you cannot, the eruption is here in the Canary Islands, but you cannot see anything, right? Because in Colab, you are seeing the full disk without zoom. But if I go locally and give a zoom, right? Canary Islands, here you have the Cumbre Vieja volcanic eruption, right? And it is right on the edge of the full disk, and that is why the resolution is lower, right? And you have shades of pink throughout the plume, right? Which suggests, according to the quick guide, higher ash content, right? And according to the quick guide, reds to magenta means pure ash, right? So we have seen that dust and ash RGBs, they use the same channels, right? Channel differences, changing only the thresholds and the gammas for the green. Okay, now let's create the SO2 RGB. The SO2 RGB. Assignment number 6, right? I will copy the script from the RMS here. Again, paste it in assignment number 6. Change the title to SO2 RGB. And I will change the date to 2019-07-1912. That is the eruption for Ubinas again. And change the bands to bands according to the recipe. And some quick guides shows the band and some quick guides doesn't show, but this one shows, and it's easier. Band 9 and 10, bands 9, 10, 13 and 11, 13 and 11, okay? They all have the same resolutions. I will read them every 4. And here I will change their names to data underscore CH9, data CH10, data 13, and data 11. Okay, 9, 10, 13, 11. 9, 10, 13, 11. And now let's calculate the recipe, right? Red band, 9 minus 10. Green band, 13 minus 11. Blue band, 13. Okay? Red band, data 9 minus data 10. Oops, sorry. Green band, data 13 minus data 11. And blue band, data 13. Okay? Let's change the minimums and maximums. Minus 4, 2. Positive, right? Minus 4, 2. Positive. Green. Minus 4 to 5. Minus 4 to 5. And blue to between minus 30.1 to 29.8. Minus 30.1 to 29.8, right? Then we clip the values to keep them everything below the minimum as minimum and everything over the maximum as maximum. And we configure the gammas, and according to the recipe of the SO2, the gammas are 1. 1. Normalization, and I do not need to invert the blue channel. Okay, now you change the title to SO2 and the image name to SO2 and run the cell. Let me create a script while the cell is running in my local working directory. I will copy a script and paste it and call it SO2. SO2. Open it with my editor, and you can use any editor you want. And I will paste. Here you have the SO2 RGB, okay? In Google Colab. And here you may see the eruption, right? But let me run it locally so you can see it in high resolution for a particular region. I will copy this. I will paste it here. Change my directories because I do not have a content directory in my local machine as we have in Google Colab. I want a high resolution image, so I will read pixels every 1. And I will also change where my shapefile is. And if you have a file in the same directory, let me close this and let me run Python script SO2. And while the script is running, let me just see if you will not get any errors. Downloading bands 9, 10, 13, and 11. So this is cool. Okay. And here we are using the standard commands we already know based on the first 2 days. Fix size, reading parameters from the header, from the metadata. So Cartopy knows how to position the maps over our plots. Reading a shapefile, adding borders, coastlines, grid lines, adding a title, and showing the RGB, right? I have retrieved the file name from my file, so I can plot the date, can insert the date in my title, right? And, My script is still running. And if you have any questions, you may send your questions in the chat window regarding any one of these commands, okay? Any of these commands. If you do not understand any parameter, just let me know. Let's wait a little bit more. And it's taking some time. And that is why when you are developing your own scripts and your own research, and it's nice to use Google Colab because you are not loading your machines. And then after you have something listened, then you test in your workstations, okay? And here you have the SO2 RGB. Here I click at the magnifier and zoom in the region I want. And here you have the eruption, okay? And if we look at the quick guide of the SO2 RGB, let me open it here. We will see that the SO2 product can be used to detect and monitor large sulfur dioxide emissions from volcanoes, as well industrial facilities such as power plants. And page number 2, right? Upper level SO2 with cold background appears as orange. Upper level SO2 with warm background appears as light yellow. And low level SO2 as light green, right? Okay. And if we change, and that's what you're seeing here. Now, in my last example, I just would like to run change the date to plot eruption in Volcán del Fuego in Guatemala. And that's 2023, 05, 04, 21, right? Let me run it again for the SO2 and for the ash for the same date. Let me run locally as well for the same date. SO2 and ash. I will save it and run the SO2 script again. And I can also open another prompt, activate my workshop environment, go to my folder, VLab, Python, goes, and run Python script ash. So I will be running both scripts together for that new date. Let me see if I have changed the date. 2023, 2023, okay? And that will load my computer a little bit, right? And this is the result for SO2. And Volcán del Fuego is here. Here it is, Guatemala. And as you see, we are not seeing an SO2 signature with orange, white, and green pixels, right? But if we run the ash script, let me see on Colab. Okay, the eruption here, and let me see on Google Colab. Here, you cannot see it very well, but let me open my result locally, and I already have it. Here, let me zoom in Volcán del Fuego. And here you have a big magenta plume, right? And as the quick guide says, red to magenta is pure ash. Okay, and that's the magic of RGB composites. Okay, and with this, we will finish our demonstrations for today. Let me close it. Let me close here. Before we go to our first demonstration, our first presentation, you have just seen how great RGBs are, right? And I just would like to show you an additional information here. You might ask how these recipes are created and how these recipes are tested and discussed, right? And here you have. In October 2022, they had the 4th edition of the RGB Developers and Users Workshop, right? And this is a global workshop with developers from space agencies, weather services, and universities. Also, users of RGB products. And it's important to coordinate and join efforts in understanding the applications of these RGBs and also create training material, organize events to be sure that these RGBs are utilized, right? And they are having impact, right? And during these meetings, they also investigate the standardization of these RGBs and also discuss new RGBs that are emerging, right? And if you want to see the recording of this event, you may access this link here, right? Let me just send this link on the chat window so you have it. You can see the recording of the whole event here. And you have RGB applications, opening remarks. Look at the amount of presentations you have, right? And I have one presentation here, data access, RGB creation and sharing resources. So take a look when you have the opportunity. It's a very interesting event. Also, a second information I would like to comment, and that I think it's very interesting to explain, also related to Guatemala, as we have just seen the Volcán del Fuego, right? As I have mentioned in the first day, we have created a task force, right, called the WMO Data Processing and Visualization Task Force. And in this task force, we have developers from many countries in the Americas. And we have created this task force to exchange information of the best practices and the latest technologies. So we do not need to reinvent the wheel, right? Because you see, our challenges are basically the same, right? We have 7 participants in this project, and I'm sure your challenges are the same. Human resources challenges, technological challenges. So the more we exchange information among ourselves, the better, right? And in one of our meetings, Joel, which is the participant from Guatemala, he presented a web page, this one here, this one here, where they are monitoring volcanic eruptions, right? And the interesting thing is that they are monitoring the radiances observed by GLOW16 over the regions where they have active volcanoes. Here you have Volcán del Fuego that we have just seen, okay? So in this case, they are not monitoring images, but they are monitoring radiance values. And they have the average radiances, right? For a particular region, right? And they subtract these average radiances from the maximum radiance being observed. And depending on the result, they know if they have an eruption or not. So this is a very, very nice example of how you may benefit from having access to net CDFs, for example, from your GeoNetcast Americas station, from Amazon, GRB, and the other receive mechanisms, right? And as you see, the solution created by Insivume in this case, right, which is the Met service from Guatemala, it's a unique solution, right? And it's not available anywhere over the internet. They have automatic alerts when they have an eruption, right? So I just added this information here ever for you to understand the benefits of working with digital files, right? Okay, now that's the introduction for today, and we are almost at the break. Let's go back. Let's go back to our presentation, right? And we will discuss how to become a GeoNetcast America's data provider. And we will try to make a demonstration and upload some test files, okay? So in this presentation, we will see, we are going to review the GeoNetcast America's global network. We will see the data providers of the system, understand the current bandwidth usage, and discuss if we could have a data provider from the Caribbean project in the future, right? And as we have mentioned in the first day, GeoNetcast is a global environment information dissemination system. It uses relatively low-cost technology, especially if you know how to assemble a station, as we have seen during the course, right? It transmits data to users using commercial satellites, as we have seen, digital television technology. And currently, the system has approximately 100 stations in the Americas, 3,000 stations in Europe, 300 in Africa, and almost 3,000 in the Asia Pacific region. And you may ask, wow, why do they have so many users in Europe? And that's because in the past, EUMETSAT used, they had a payload in Meteosat 8. I can't remember exactly the satellite. They had a payload directly in the satellite, right? So they had a direct readout technology, and users needed to point their antennas to Meteosat. However, that transponder failed for some reason. And then they needed to use commercial satellites to rebroadcast information from Meteosat, right? And then they started using GeoNetcast as their primary means of getting data. And that's many years ago. And that is why they have so many users there, right? The system was idealized by GEO, the group on Earth observations, and that is why it is called GeoNetcast, okay? In the Americas, we have the GeoNetcast America system provided by NOAA. In Europe and Africa, we have the EUMETcast systems provided by EUMETSAT. And in the Asia Pacific region, we have CMA-cast from the Chinese Meteorological Administration. We also have, as mentioned in the fourth day, we have another system called the Himawari-cast, provided by the Japanese Meteorological Agency. However, Himawari-cast is not part of the GeoNetcast network, right? It is just a system, a delivery mechanism created by GMA, but it's not under the Geo ecosystem, okay? And these systems may exchange data among themselves, right? And as we have seen, EUMETSAT is one of the data providers from GeoNetcast Americas. And EUMETSAT uploads part of the data that is also available in EUMETcast in GeoNetcast America. So this is a global network, okay? And as we have seen, this is the architecture of the system. And in the beginning of the upload chain here, we have the access from NOAA, that are the managers of the system. We have other GeoNetcast systems like EUMETcast, for example. And we have the data providers. And we currently have 12 data providers. Some of them are uploading content since the beginning as NOAA and NPay. And some of them joined the team recently as Sierra or SIMS. And these data providers here, they upload their data to the system using the FTP protocol. These files are received in the uplink system, and this uplink system is in Georgia in the US. And they have a data management system server and datacast software. And the datacast software here is the fast datacast server, okay? And that is why users here need the fast client. And this data is encapsulated by the fast server and modulated to the DVB-S2 technology. And after that, the data is uplinked to the Intelsat 21 satellite at 58 West, right? And rebroadcast to the community in 4080 megahertz or C-band with a data rate of currently 20 megabits per second. And this is a photo of the uplink, right? The antenna that uploads our information or the information from the data providers to the satellite, okay? And all users that are in this covered region here, including Nitio France, as we have seen in the second day here in Europe, they receive the data, right? And right now we have approximately 100 users, as you see here, and the uplink station is here in Georgia, okay? Here. All right. And here we have the team, the data providers, right? SIMS from the US and Sierra, okay? Conai from Argentina, Comet, Raynet from USA, UMETSAT from Europe, MPay from Brazil, where I work, IMN from Costa Rica, MAR from El Salvador, the US National Weather Service, right? Of course, we have NOAA and US Environmental Protection Agency. And as I said, some of them are uploading content since the beginning, and some of them joined the team recently. And to me, the ability to have regional data providers without any format restriction using a satellite broadcast is one of the best capabilities of the system, and we need to explore it more with you, with the community. Here we have some of the key products, right? It's not all of them, but some of the key products broadcast by each provider, right? SIMS, the Cooperative Institute for Meteorological Satellite Studies, they broadcast VIRS data from the NOAA 20 and SUMI NPP satellites. They broadcast 11 bands of 750-meter resolution and 3 bands of 375-meter resolution for this area in the image, covering most part of the Americas. And they use data from 5 direct broadcast LEO stations, 2 from Brazil, and the other 3 from the US, right? This one, it's not in the US, it's also from the US, okay? Okay. Sierra, and SIMS also broadcast the flood mapping products, which are 5-day accumulated VIRS composites, and also hourly ABI composites. They also make a combination of ABI and VIRS products, also covering this region here in the Americas, okay? Sierra also broadcast the flood mapping products. Sierra broadcast the ALPW product. Here is the Cooperative Institute for Research in the Atmosphere, and they broadcast so-called advectively blended layered precipitable water products, or the ALPW products. This product provides a 4D description of moisture in the atmosphere in 4 vertical layers, as we're seeing here, right? Here. Surface to 850, 850 to 700, 700 to 50, and 500 to 300, right? And based on the community feedback and what I see during the regional focus group sessions, this is a very useful product, right? And you have the HDFs, meaning that you can process this product for any region you want using the any color scale you want and make any manipulation you want, okay? Uh, and we are going to see how to process this product in the Python hands-on, okay? Um, now that we know that the basics of Python, we will be able to explore more products. And we have a question here from Eugene. SIMS data, such as the 200 millibars vorticity, do they get it from GeoNetCast or another source? This one? Well, this product here, they produce it locally. And I'm not sure how they produce it, but they are producing it locally. They use the data sets they have at SIMS, right? However, if you want to, and this product here is not available in GeoNetCast Americas for now. However, you may request. NOAA is open to hear the suggestions from users. More than that, they want to hear your suggestions. So I don't know the sources, the data sources they use to produce this product here, Eugene, but you can receive the digital files of these products through GeoNetCast in the future if you request it. Okay? Thank you for your question. All right, so Cicera, and talking about, thank you, Eugene. And talking about the capacity building activities, talking about flood mapping product and the ALPW products, usually every 3 months, we have the GeoNetCast America's user group webinars. And during these sessions, among other information, the data providers present information about their products, like applications, case studies, limitations, etc. Here on the left, you have a presentation from SIMS about the flood mapping products, right, from May 2020, and right at the beginning of the pandemic. And on the right, you have a presentation from NOAA about the ALW product presented by Jose Galvez, right? And you may access all these presentations here at the blog at GNC-A Product Usage Trainings, and I'm going to send you the link so you may access it. Just a moment. There it is at the chat window. And if you access the blog here, here's where you may find them. User interaction, product usage trainings, okay? And here you have some of the trainings, including the ones from covering the flood mapping products and the one covering the CIRA's ALPW product, okay? Just to quickly show you the presentation from the flood mapping products here, right? So you have an overview of these products, list of products that are available, the capabilities, composited products, the coverage area, right? The coverage area, some other details, how these products can be used during the day, some limitations or issues to be aware of, and some examples. Flooding in Brazil, flooding in Canada, contact information and references, okay? And here for the ALPW, you have what it is, right? Advectively blended layered precipitable water provides a 4D description of the moisture in the troposphere in 4 vertical layers, okay? The basics, how you may access them, how these products differs from the conventional precipitable water product, right? How it is generated, and it is using mirror soundings from different satellites, winds from GFS, and some other information, right? The advantages and limitations, and some applications examples. So this is the kind of presentations users have, okay? And that you may find available in the GeoNetCast blog. And if there's a specific product available in the system that that you do not have a presentation there, you may request that, and we can coordinate. This presentation with the data providers. And here you say how high. There's a question: how high can the resolution get? For example, would be able to generate image for Grenada without it being pixelated? Well, as it is written here, they use microwave information from the mirror sensor, right? And these microwave information, as far as I remember, they have 12 kilometer resolution or 15 or 20, something like that, right? Because that's the resolution of the sensor. And that is why images are a little bit pixelated. However, I'm not sure if they can increase the resolution of this product, but it is totally possible for you to plot this information for Grenada. However, they will be pixelated. For example, if you access the GNC-A station from El Salvador, they are plotting this product for Central America. Okay, and as you see, yes, that the image is pixelated. However, that's the maximum resolution of the sensors used to create this information. Okay, and we may ask the providers if it is possible to create images with higher resolution. The data providers are open for suggestions and discussions. Okay, so you will be able to change this area here, another location, but the data will still be pixelated. Okay, thank you. All right. We also have some other regional providers like CONAI from Argentina, which is the National Commission for Space Activities, and COMET RAINET. And RAINET is the radio and internet for the communication of hydrometeorological and climate-related information. And both of them broadcast model information and forecast charts, right? We also have EUMETSAT, and EUMETSAT broadcasts data from the Meteosat second generation satellite, like the Siberi sensor bands and some derived products. And also many other data sets like ASCAT winds, sea ice, sea surface temperature, fire monitoring, atmospheric motion vectors, cloud mass, cloud top height, global instability indexes, accumulated precipitations, soundings, and much more, right? And here at NPE, where I work, right? Currently, we broadcast hotspots from many satellites: GO16, METOP B, NOAA 19, NOAA 20, NPP, Aqua, and Terra. We will also see how to plot this information, probably next Monday, okay? This is a shapefile, and it's not hard to process, as we have seen. We also have IML, the National Weather Institute for Costa Rica, and MARN, the Ministry of Environment and Natural Resources from El Salvador, and they broadcast model information as images, as PNGs, and or digital information as BRIB files, right, from MARN. We also have the USA National Weather Service, and they broadcast the so-called International Services and Communication Systems, or the ISCS. And the ISCS systems are part of the RA4 Regional Meteorological Communications Network, RMTN, and they focus on delivery of critical and routine watches, warnings, observations, and forecasts. And that's what they provide in GeoNetcast. They have 12 different product sets or subfolders that are available in the GNC-A data stream. And in total, there are over 16,000 different products like METAR, forecast summaries, watches, warnings, advisories, and much more. So if we look here at the MARN's webpage, for example, are just using this information, the tropical weather discussions, as you have seen here, and tsunami warnings. Last tsunami warning was from 24 April 2023, right? And they also used the volcanic ash warnings. And the last warning was from April 30, okay? And of course, we have NOAA, right? And NOAA is the main provider of the system. And they upload goes east, goes west, both ABI and GLM, many products from the JPSS series like blended TPW, active fires, ocean color, as you are going to see later, vegetation, ozone, rain rate, sea surface temperatures, new caps, mirrors products, microwave imagery and products, and much more. Okay. We have a question. Are you familiar with the Vitra platform, Diego? I have seen some presentations from KSEN, right, about the Vitra, and it seems to me a very good platform. And I wonder, and I think you can use the digital files available in your ground stations to add information to this platform. That's probably possible, and you can integrate this information to the Vitra. Probably, I don't know the tool in detail, but it's possible. You have the digital files. You have the NetCDFs, RIBs, text, shape files, HDFs. You can do anything you want with them, and that's the main aspect of the systems. And some of the data providers are uploading data to the system since the beginning. And in the beginning, we had 10 times less capacity than we have today. And that's why some years ago, an initial selection of products has been made. However, with time, and based on the user product requests and requirements, the content of the system has been modified and adapted, right? And talking again about capacity building examples, for the products uploaded by NOAA, we have had many trainings during the user group webinars. As you can see here, we had an introduction of to the JPSS data products, volcanic ash products, the VIRS ocean color products, vegetation products, and the GOES data collection system platform. So we had several trainings throughout the years, okay? And as we have mentioned in the first day, this is the bandwidth usage by broadcast channel, okay? And most of the system capacity is used to broadcast the GOES 16 bands, okay? As you see here, this is by the channel that uses more bandwidth in a sequence, right? And the higher resolution bands like the 0.64 and the 0.86 micron, for example, band 3, or the 1.51 micron, band 5, they occupy more space because the files are bigger. Also, the VIRS band, as you see here, right? The VIRS band are also huge, okay? And if you look here, you see the number of files transmitted every day, more than 127,000 files in average, okay? Another information is that the daily bandwidth utilization is actually an average of approximately 50%, right? However, that doesn't mean that 50% of the capacity is available for use. That's not the case, right? Because 50% is a daily average. If you look at the usage every hour, you see some daily peaks around 17 UTC. And if you pay attention, depending on the day, right, at 17 UTC, sometimes we almost reach 100% of the system capacity. This is the system capacity, and this is time, right? And this is approximately 17 UTC. And now I have a question, and please be ready to answer this question in the chat box, okay? Do you imagine why we have these peaks at 17 UTC, right? Like here, we have all these peaks. Do you imagine if we are broadcasting the same files on and on during the whole day, why do you have these peaks in the afternoons? Do you have any guesses, or you may send your suggestions in the chat window, right? If you have an idea of why that happens, right? Oh, and by the way, here's the amount of data you receive every day. We are using, for example, 20 megabits per second, and that is equal to 216 gigabytes per day, or 78.84 terabytes per year, right? We have an answer from Daniel. Thank you, Daniel. Latency peak. That is right. But why that happens? Why do we have more latency induced at 17 UTC? Do you imagine why the cause of this latency? If we are broadcasting the same files on and on, why do we have these peaks, and which could induce a latency? I will give you some more seconds for you to guess. Okay. And the answer is that around 17 UTC is where we have the goes east footprint mostly illuminated by the sun, right? And therefore, the files from the visible bands, like bands 1 through 6, they are much, much, much bigger than during the night, right? And that's why the bandwidth usage during the night is much lower, as you see here, right? So the managers of the system, they need to be very careful when adding new content to the broadcast, okay? Talking about these peaks here, let me just open the presentation from the complementary activities so I can show you one graph. If you go to Moodle, let me go to Moodle now. Here. If you go to Moodle and open the presentation available here in the complementary activities, here, Introduction to Satellite Product, Data Access Mechanisms, and Visualization Tools. You see this presentation here. By the way, let me just give you an overview of these slides, okay? I'm not going to present them because there's too much content, but you may use them as a reference in the future. First, you have some fundamentals, right? We also have some recent satellites and products, an overview of the data access mechanisms and visualization tools. And we start talking about orbits, right? GEO and LEO, some simulations you can do the internet, you can change the orbit, you can simulate orbits to understand the concepts better. Then you see the recent satellites and products like GO 16, 17, 19, and 20. You have some photos and information on the instruments, right? What instruments does NOAA 20 and 21 have? You have a list here, right? And you have some product examples. First, for JPSS, for ATMS sensor, CRIS sensor, UNT sensor, and VIRS. And we will process this VIRS information in the last day. day-night band, and so on, right? And here you have the true color, the RGB that Wayne is trying to create using data from GOES. We also have introductory information on GOES. Have all the instruments here, recent launches, all the instruments and products, SUV, magnetometer, axis, GLM, ABI. We also make some comparisons of the GEO and LEO orbits and scans, projections. Here we have the same scan in the cylindrical equidistant projection and the GOES-R projection. How we can change that, we are going to see after the break, okay? And you also have information on the LEO and GEO orbits. And here we compare the orbit from JPSS and GOES-R. And as you see here, while it takes 10 minutes for the JPSS satellite to make this trajectory, 10 minutes, GOES-R has already made a full disk scan, okay? And here we have the graph I would like you to see, right? This is a graph of the number of megabytes received during 24 hours, only for GOES 16, right? And here you see that we have more than 6 gigabytes per hour. And we have a peak here. Here's our per megabytes. And here around 17 or 18 UTC, depending on the time of the year, we have much more file. The number of files are the same, but they are much bigger because the footprint is fully illuminated, right? We have more pixels with information, right? For example, if you go to DSAT and select, for example, an image for 17 UTC, for example, from yesterday, May 11, 17 UTC. And select, for example, band 2. Here you have most of the footprint, or the entire footprint, 98% of the footprint is illuminated, right? However, if you go to 4 AM, most of the footprint are dark. And thus the netcdf files will be much smaller because they contain less information, okay? And if you go, for example, to 13 UTC or 11 UTC, or now let's see the last image for today. Let me open it again and change it to band 2. So you see here, part of the footprint is dark, so the files are not that big as it is in the afternoon. And that's the case for band 2, band 1, band 3, band 4, 5, and band 6. Okay, and that is why even if we have an average daily use of the GeoNetcast transmission of 50%, we need to consider these peaks in the afternoon. Okay, because depending on the amount of data we have, we could saturate the broadcast and generate queues. And before we return to the previous presentation, let me just show you the kind of information we have in these reference slides. We have a description of most of the data reception mechanisms that are available. And we talk about cost, latency, right? If internet is required, the data available in each one of these systems, right? And we begin with GRB, the GOES rebroadcast, right? Coverage, station, kind of data, instruments, content, community, and so on. And here we have a summary: cost, latency, internet, and data type. We also have information on the H-grid N-wing system. Same information: community, cost, etc. GOES DCS, or the GOES data collection platforms. LEO high-grade data stations, or direct readout stations, right? Community, summary, GeoNetcast. And here we have basic information we have seen in the first day, including the coverage, etc., and a summary of the products that is available in GeoNetcast. Okay. We also have NOAA's Big Data Project, or the Open Data Dissemination System program, right? And because this program exists, that's why we are able to download data from Amazon using our scripts, right? And that's something new. And it wasn't available in the previous generation, and it made things much easier for us, right? We can use this data as our primary source. If you have the bandwidth, internet bandwidth, right? We can use it as a backup. We can use for research, so it's amazing. We also have mechanisms from Unidata, right? Like Makaidas, AWebs, IDD, etc. And we also have the archives, right? From NOAA and UMetSat, and for NOAA, it's the NOAA class. We want to download data from the 80s or from the 90s. Here's where you need to go. I remember some years ago, one of our users here in Brazil needed a data set from the 80s for his research. And of course, we didn't have this data in our servers. So we created a tutorial and sent this tutorial for him so he could access these data sets from the 80s from NOAA. And he was able to do that and open this data set with Makaidas, for example. Okay. You have a link for a tutorial. And you also have the archive from UMetSat, which is called the UMetSat Data Center. And you have the whole series from Meteosat, JSON, METOP, and the other satellites, Copernicus and the other satellites, right? We have the web pages, some suggested web pages like Cirrus LiDAR, DSAT, and the CSPP Geosphere. They use similar technologies, but they have subtle differences, right? And we also have a couple of links with a lot of information. And these links have been created by SIMS. They have dozens of links with visualization, data access, and capacity building resources. We also talk a little bit about GeoXO satellite, the next generation in 10 years, right? And we have a summary of each one of these mechanisms, the advantages and disadvantages of each one. Okay. And we finish these reference slides with some visualization tools, right? If they're able to process local data, remote data, or data available in the cloud. So we have the IDV, Makaidas V, WCT, SIFT, which is an amazing tool for education. And of course, Python, as we're seeing, MatPy, and Showcast. So we finish with other resources and a conclusion, and the training methodology, as we have seen every day of this training. Okay, so this is a reference slides that we have in Moodle. You can use them as a reference in the future. Okay, now returning to my presentation. For each data provider, an IP and a password is provided, so they can send data to the uplink server, right? Also, there's no format restriction, and in the future, you may broadcast any information you want, as long as the system is able to handle it in terms of size and frequency, right? And there must be some coordination between the possible data provider and NOAA. Okay, now we are going to the break. Okay, and after the break, I will make a demonstration and upload a test file or some test files to the system so you understand how the upload process works. And the file will travel from my computer, the uplink server here, the satellite, power stations. Okay? Now we are going to the break. And We will return in 15 minutes, okay, at 10:30. And if you have any questions, just let me know. Thank you. See you again in 15 minutes for the demonstrations. All right, let's return from the break and let me open my slide here. Just a moment. Um, Now let's try to make a demonstration. Okay, I will try to upload a file from my laptop and upload it to the system. Let me just open our online station. Let me close some tabs. I will access our online station from Synth, and I will send it on the chat for you. Oops, where is the chat window? Okay. The link I have sent in the chat is the same link we have used it. Just a moment. We have used it in the first day to access a remote GeoNetcast Americas station from Synth, right? And here it is. You may see all the ingestion directories from that station. And in the first day, we have downloaded some information. We have opened these files with NASA Panoply. Remember that? Now I'm going to access this folder here from NPay. Let me reload. Sometimes the connection is slow. Let me close it and try it again. NPay. Okay. And this is the ingestion folder from NPay. And as you see here, you have some shape files. When I click here, for example, a shape file will be downloaded to my machine. But these are compressed. So I just need to uncompress them, unzip them, and you see a shape file, which is uploaded every hour. And in this shape file, you have hotspots processed from many satellites, as we are going to see next Monday, right? But what I would like to show you is this here. Yesterday, in the last days, I have uploaded some test files just to test if I would be able to upload information from my notebook, okay? And I'm going to try it now. Sometimes it takes a while because it depends on the number of products being uploaded by the other data providers at the same time, right? So I have a folder here in my computer. It is called Upload GNC-A. Okay, could you please just confirm that you are hearing me well and that you are seeing my screen and that everything is going okay? Would you please just send an okay in the chat box? Okay, okay. Thanks, Wayne. So here I have some files, okay? And I will copy this text file and I will change the name of this text file. And I call it May, well, today is 12, right? May 12, it is called test file 2023, May 12A. I will open this text file and I will put it here. Hi, this is a test file. And today is May 12, 2023. And now it's 14:45 UTC. GeoNetcast America's Eastern Caribbean Training Workshop 2023. I will save it. And I will upload this file with a bat script. But I will not display the bat script because I have the IP and the password. So I will hide it and I will change it. And I will insert the name of my file I have just created here in this bat file. Okay. And I will run this bat script here. Okay. I will run this script. Right? And the file has been uploaded to GeoNetcast Americas. And here you have it. Test file 20 at 12 at 20 here. May 12, 5A. Hi, this is a test file, and today is May 12, 2023, 14:45 UTC. GeoNetcast America's Eastern Caribbean Training Workshop 2023. You see that it was almost instantaneous, right? It was immediate. So, the file went from my notebook, right, to Georgia, to the teleport, to the satellite, to the station from SIMS, processed by the receiver, by the CANcast, and it was in the folder, in the next couple of seconds. Okay. Let me now. I have another file here, and this file was shared by Wayne. Thank you very much, Wayne. And here Wayne is processing the day cloud phase composite, RGB. Okay. You may see here that he put a title, another title, the coordinates, CIMH logo, a very nice image. Thank you for sharing, Wayne. And this image is called test G16 DCPR RGB underscore EC, etc., etc. Okay, what I'm going to do, I'm going to copy the name of this image here, and I will put it in my bat file. Okay, let me just hide it and edit. I'm editing it now. I'm inserting the name of this file shared by Wayne, saving my bat file, and uploading it. Here you have the log, okay? And the file was uploaded. It could take some minutes, right? It is not, oh, here it is, test G16 DCP RGB, the file that it's in my laptop here. Okay, it was received. And I'm using the folder from MPay because we are one of the data providers of the system, okay? And now we are just simulating that CIMH is one of the data providers of the system, right? We are just making a simulation. And if we click here, we should see the image open in our browsers. It's taking a while. Let me reload and click it again. And here you have, okay. And now I'm going to get the second image. Let me see if this is the one. I will upload this image now. I will paste it. This is also created by Wayne. I'm going to paste it here, copy the name, and it's called G16 PRC RGB, the name that Wayne chosen in his Python script. And I'm going to edit my script that uploads data to GNC again, save it, and run the upload script. And the upload script is running, right? And it took 2 seconds to transmit it. 2 seconds using my internet and my computer here. And pay. It's not there yet because, as I said, it depends on the number of files being broadcast, okay, for a certain period of time. So after that, we will check it again, and let's see how much time it will take to reach the user station, okay? But what I would like you to understand is this. Let me return. That any of your services may become a data provider in the future, right? But we need to coordinate with NOAA, and you need to have products that are useful for your community, right? This is how I have done this, right? Let me just explain for you the upload procedure. When a data provider is approved by NOAA, right? NOAA will provide an IP and a password, and I'm not showing them here in these screenshots, okay? Right? But here you may see that we are just connecting to an IP address, and here I'm using a batch script. I'm using a Windows batch script. But if you are data providers in the future, you can use anything you want, right? At NPay, our IT staff, they use Linux bash scripts. And here I'm just demonstrating with a Windows script. So we open this IP, and before that, I'm just, if I have a file called image1 PNG, I use a rename command to convert the extension of this file to .png to .png.pnp, because this is one of the requirements from NOAA at the server, right? So I'm opening this IP, entering my channel, which is called NPay in this case, and I'm inserting the password that NOAA has provided us, right? According to the procedure, the data provider must enter in a subfolder called hot, which is a subfolder inside the server. Put that temp file inside this folder, this hot folder, right, with the TMP extension, right? And after the file is already there, the provider needs to rename it, remove the temp extension to the original extension, and then this will finish the transmission, right? And after that, I have quit the connection. So with this simple batch script, I have uploaded a file to GeoNetcast Americas. And this file is available at all the workstations, right, inside NPay's folder, okay? And here you have a log with what I have done, right? Connection okay, transfer complete, file change, renaming okay, ready for destination name, rename successful, upload finished, transfer complete. Okay, right? And here we have seen that the files I have uploaded from my computer, the uplink server, right? It was sent to the uplink server, the geostationary satellite, right? It has been received by the antenna, processed by the VPS2 receiver, and encapsulated and managed by the fast client, right? And then it was moved to the injection directory, and it was made available for users. Okay. Now let's just make me a final verification here. The file that we have sent, let me refresh it. sorry, wrong provider. Anyway, the file that we have sent, it's not here yet, the last file, but first file, this one, and the second file, this one, is already there. And I will check it again later to see if the last file we have uploaded with the true color composite will arrive, okay? As I said, it depends on the number of files being broadcasted. So it enters a broadcast queue and it is received sequentially at the user stations, okay? All right, so the objective of this presentation is this, right? You understand that it's possible that your services may become a data provider of the system in the future, and that with some coordination, you may upload your own files to the regional community. And we have seen that each provider uploads the data sets. We have seen which data sets are uploaded by each provider. And we have finished with a demonstration, so you understand the whole process. Okay. Now, let me just open. Before we go to the next presentation and learn some new tricks, in the fourth day, we have seen the fast client in detail. What it is, how it works, and what it is, how it works, and how to install it and configure it, right? And now that I have the credentials to access the station from Granada, I just would like to make a quick demonstration, right? To show you the fast professional client in action. Let me open the window here. And here you have it. I'm accessing the station from Granada, right? Let me increase the zoom. And this is the Proteus software processing data from goals. And here you may see May 12, 4030, from May 14, 4030 to 4040, right? And here you have a list of products it is generating, including the full disks. Okay, and here you have Showcast. And if we access the browser at localhost port 4039/admin, we will see the fast professional client. Okay, let me increase the zoom a little bit. And this is the client, the Scancast's client. Okay. If we access the main page of the fast client, you will see here the files that are currently being received. As we just have tested in the demonstration, the providers just sent these files here, right? Goals 18, band 2, band 9, band 13, goal 16, band 2, and this one is a big one, right? That is why our file was taking some time to load, to be broadcasted, right? And apart from that, you can see the number of received transmissions in the last 24 hours and the number of missing packets. In this case, 0%. 40 packets, but in comparison to the total transmission, it's 0%, which is excellent. We usually recommend at least less than 1%. Okay, so this is great. We also see here that we have no alarms, which is also good, because usually when you have an alarm, that means that something is wrong. Okay, so the fast client is running perfectly in this station from Granada. If we go to configuration, channels, right? You see a list of broadcast channels, right? And you see that all of them are active. Here, NPay, UMETSAT, KONAI, NOAA, etc., etc., etc. We have seen, look here, Caribbean Meteorological Organization, CMO, in the past, right? We have made some tests, right? And we have even created a broadcast channel for CMO. However, we didn't finish this project, but it's time to restart it again, right? And you can see here this huge list of channels that are active in this station from Grenada. Okay, but we can, for example, you may see that there is a broadcast channel for each one of the ghost bands, and you can enable and disable them if you want, right? If you want to disable some bands to spare disk space, for example, you may just disable it because you may disable bands separately, okay? And if you go to configuration, receive settings, virtual paths here, you see that here EEC, which is the vendor of the station, configured where they want to store the data. ESS, data, satellite, fast. But you may select any folder you want. If you click here, for example, you may change it and say, all right, okay, I'm not going to change it because EEC is processing these files, and if I change it, the station will not visualize data anymore. If you go to license here, you see your license number. In this case, 173234, right? And they call it site ID. This is the unique identification of this station, right? If you go to statistics, statistics, channels, and channels graph, you see, right, the channels that are currently receiving data. And each channel has a different color, okay? So right now, this channel here, light green, which are the flood products from CIMH, they are broadcasting information. Okay. Also, if you go to logs, here, logs, and received files, it is loading because there are hundreds of files. You see last files that have been received, right? And here you have the date, May 12, 15:03 UTC, which is the current time, right? So you can see all the files that have been received. And you can go to the next page. And so on. Let me go up. And you are seeing many text files, right? And these are the alerts from the ISCS channel. Okay. Here we have number 13 from goes 18, alerts, etc. Okay. If you go to documentation here, you will be able to access the admin guide provided by KenCast, right? Sorry. Here. Okay. And you have all the information you need to manage this software. But as you see, in the end, let me go back to the first page. In the end, it's a simple software. Okay. And this is the most important page of the software, the first page, because it gives you crucial information. Okay? Now I would like to make a second demonstration. Just a moment. Oh, and by the way, if you access your stations, that's why I wasn't seeing the file here, because it starts with a G, the file that was created by Wayne. So it was the first file in the list. So it was already there for 10 minutes. And if you click, you see the file developed by Wayne, right? And it has been received and broadcast, okay? Now, the second demonstration I would like to make is the fourth day, we have seen details of the workstations, the processor, memory, hard disk, and the other specifications, right? So I just would like to make a quick demonstration. Let me open here, right? Let's check some of the specs. So I'm going to open the terminal. Let me check the processor. So as you're seeing here, this is a 10 core where here, Xeon Silver 4210 CPU running at 2.4 gigahertz. Okay. Here, LS CPU. So here, 10 cores per socket, but we have two sockets. We have two sockets here, two sockets with 10 cores per socket and 2 threads per core. So in the end, I have 40 threads, okay, running. I'm going to show that later. Let's see the memory. Just a moment, grab mem total, doc, mem info. And you may see that we have approximately 65 gigabyte RAM, right? And if you look at the storage, DF-8, we have, this is the data acquisition workstation. We have 2 terabytes for storage. Okay. Now let's check ingestion directory, which according to the CANcast software, as configured by the vendor, EC, it is ESS data satellite fast. Let me list it. And here you have all the folders from GeoNetcast Americas. The same folders from the station from Sims, because they all receive the same data, okay? And if you enter, for example, CD NPay and list the files, you will see the files that we have uploaded in our demonstration. The text file, the test image, and the image created by Wayne. Okay. What more? What else? Here you have Proteus, the software developed by EC. Let me go return to 75% now. Let me open the last full disk scan. And as you see here, it's from 1450 to 15 UTC minutes ago, right? And if you click here in the list of products and load product, the product will appear in a new window. Here, okay? And you have a lot of options here in the upper, and you can manipulate it, and you may make calculations, etc., right? I'm not an expert in Proteus. However, I understand you may configure it to process and visualize a list of products according to your needs. And the images will be automatically updated. And you can also load multiple products in multiple windows. Okay, so as they suggested, in the data visualization workstation, you can have up to 4 monitors. So you may configure Proteus to display a group of products in each screen, right? And you have a very, very nice interface for real-time monitoring, okay? I really suggest that you learn how to use Proteus. It's a very, very powerful software. Let me minimize it. And here you have Showcast, as you're going to see next Monday. And it's also processing these products using Python, as we have learned it throughout the course. Here you have the bands. Here you have baseline products. For example, cloud top height. Here you have everything processed with Python. Cloud top temperature. This is for today, okay? Cloud mask. Cloud phase. Cloud aerosol optical depth. Cloud optical depth. Cloud particle size. This one, oh, cloud top pressure. And here, sorry. Here we have, for example, the derived motion wings. And look that it is, I'm using barbs here. Remember from the last day that we have learned how to plot the barbs, plot the winds from GFS. So here we have the derived motion winds product, and I'm using the barbs to plot these barbs from different levels. Okay. We also have GLM and many other products. Meteosat, right? This is Meteosat imagery. And this is from a couple of hours ago. And here you have the station from Granada. Okay. EGPY. I don't know why EC has configured it like that. I don't know the meaning of that acronym. You have LEO data. So this is microwave imagery from today, May 12. Okay. From LEO satellites, from in this case from GCON W1. Blended rain rate, microwave blended rain rate, blended total precipitable water, SST anomalies, sea surface temperature and sea surface temperature trend. Here you have the Sierra advected layered precipitable water, but in this case, The vendor hasn't configured for your region, but you can do that easily, and we will see next Monday how to do that. Okay. You also have an interface with hotspots. Let us wait for it to be displayed. And this is a very decent machine. And here you have fires and hotspots detected. And by the way, this is the product from NPay. Okay. So Showcast processed that shapefile that is available in the NPay here. These shapefiles here, they have been processed by Showcast. So the system unzipped it automatically, processed it, and it has created this very nice interface. Let me change the background. Let me add states, countries. And here you have all those spots. And if you zoom in, let me zoom in. Here, if you click at a given pixel, you see some information about it. But you should see more information. The problem is that I'm remote accessing it, so the pixel is not loading, but you should see when you click at a given point that satellite, the time of detection, etc., right? So this is available in your stations. And by the way, this interface here was created with Python. This nice interface has been created with Python using a library called Folium. If you go to the blog and seek for example, Folium, I have created a blog post a couple of years ago, right, called Learning Folium with Fire, and I show how to, here is what you should see. The satellite, the date, the time of the detection, country, province, and city. And here I have an example script on how you can create a nice page like that using Python alone. It's great, okay? All right, so this is the station. Let me go back to the main page. Bands, yes. Let me close this window here. So this is what you have available. Now let me see the system monitor here. Applications, system tools, system monitor. Is loading. Let me see if it is already open. Oh, it's already open. Here it is. This is the system monitor, okay? Here. And you may see all the 40 threads of your processors, right? And approximately 60 something gigabyte RAM, right? 62 for the memory and 4 for swap. And you also have the data visualization workstation. This is the data acquisition workstation. So in each ground station of the project, you have, as you have seen, powerful machines, right? Powerful workstations. And I really suggest you to configure Proteus so it displays automatically the data sets you want. And as you have seen, you may add 3 monitors more in the data visualization workstation. You may configure Proteus to display in each monitor a different product and a different set of products. You also have Showcast. And just a final comment on Showcast, it is not the latest version, right? So you need to update it in the future to display more products. And we will talk about it next Monday. These products, keep being processed and visualized even when there's no internet, because they don't need the internet to be processed and to be received. And even during a power outage for a short period of time, according to the autonomy of the UPS, we will still be able to visualize this information. So you have a very powerful tool in your hands for disaster resilience, for example, right? And apart from that, with the data available in the workstations, which are easily accessible, you may create your own products with Python, as we are learning. And as we have seen, you may upload these products to the system and to your web pages. So you have everything you need to make the best use of the data. And I have shared these specifications of your workstations with some colleagues, and they were impressed. You have very nice workstations. And I really suggest that your developers and your staff explore the workstations because, for example, in this acquisition workstation, I'm accessing Proteus here, but it is basically because it is being processed in the second workstation. But I'm basically just receiving data from the CANcast software and EC is making a pre-processing of this information, and that's it. I'm sure you can use this workstation in the future or the other workstation to add some more processes to create your own products with Python. So you need to explore these workstations. You already have your products being generated here, but I really suggest that you explore them and make the best use of them. Okay, so you have two workstations like this one, and the second one is even better because you have 4 terabytes of disk space. You have one of these in each service participating in this project. Okay, and the last demonstration I would like to make is that, and now let me enter the edition mode. In the end of the 4th day, we have seen or in the middle, after the break, we have seen this maintenance checklist. And I would like to show this maintenance checklist and fill this table with you. So we may see the status of your reception. And this is one of the assignments in the Moodle webpage under day number 4, right? So I'm going to make a demonstration, and I really would like you to check the same parameters in your ground stations, right? Oh, thanks, Eugene. That's our airport locator. So EGPY is the airport locator from Granada. We send out our aviation data using that identifier. Great, thanks, Eugene, for that information. He's talking about this identification, for example, here. EGPY, okay? And as we are going to see in the Python hands-on, it's very easy to add labels like this one. Okay. What I'd like to do now is fill this table with you, right? I like to check some of the parameters of my ground stations, right? And I would like you to do the same when you have the opportunity or when you have access to your station. And these are some critical parameters that you need to check, right? For example, is the receiver working? Is it on? The power LED is on. If we look at the remote workstation, look at the receiver management console here, you see a green status button. So it is working, right? Okay, status on, power LED on. Is the signal locked? Is the lock LED on? Data, signal. This signal is the lock button. Let me increase this here. If the signal is green, the GeoNetcast signal is locked. Okay. Lock on. Is the receiver data LED blinking? Is it communicating with the fast client? I do not have the receiver here, an image of the receiver here, but as you may see here, packets being processed and packets sent. and the data is green. So the receiver is communicating with the fast client. Okay. Okay. Data blinking. Let me just change this. Nada. Okay. Ha. EGPY, right? And okay, what's the receiver carrier to noise ratio? Carrier to noise, 12.5 dB. 12.5 dB. Is it more than 10? Yes, okay. What is the receiver signal strength? Minus 38 dBms, right? Minus 38 dBms. 38. Is it around minus 40 and minus 35? Yes. Okay. What is the L-band frequency configured? It must be configured to 1070 megahertz. 1070 megahertz, right? 1070 megahertz, right? Received symbol rate must be around 30 megasamples per second. And here you have 29,999. 29,999, right? Uncorrectable rate, right? The lower the better, ideally 0. And here we have a very low number, 1.090. 1.090. Do we have any alerts in the fast client? Let's check. Fast client. Do we have any alerts? Or alarms, sorry, not alerts, alarms. 0. Okay? No alarms. What is the missing packets in 24 hours, in the last 24 hours? 0.0%. And lower the number of packages losses, the better, 0.0%, right? Is the fast client receiving files normally? Logs, received files. Let's see. The last file has been received May 12, 1527 UTC, right? So yes, receiving files normally. The IP interface is available in the fast client. Configuration, receive settings, channels defaults. It should be or either all or the Ethernet IP of your network card. So it is here, it is available, right? So you do not have any networking problems, okay? Is the fast main channel active? Channels, main, and that's the main channel. You must not disable it. It's active. If you disable this channel, you will stop receiving everything, okay? Active, right? Are the desired channels active, right? The channels you want to receive must be active. Oops. Here, they're all active, okay? All desired channels are active. Do you have space available in your hard disks? Let's check. Terminal, EF minus H. And as you see here, right now, you are using 80%, right? 80%, this mounted here, and 87% here. And satellite is where, as far as I understand, is where EC is configured the workstation to receive the raw data. And processed is the folder where they have files that Pro Tools you use in the next workstation, right? So they make some pre-processing here. This number is huge. However, PC has programmed or has added some from routines to delete files routinely, right? But you need to check. If it is 100%, if it reaches, especially this one here, if it reaches 100%, you see an alarm on the fast client here, active alarm. And then it will say, hey, I cannot store files anymore. Okay. Yes, let me put here 80% satellite and 87% products. General notes, just as an example, last verification, May 12, 2023, 15:30 UTC. So this is just an example, okay, guys, just for you to understand the critical parameters that you need to monitor to see if everything is running well, okay? This is the objective. And let me just open the presentation we have seen on day number 4 called maintenance aspects. And you have a flow chart here, right? If a gesture stops, the first thing you need to look at the receiver. That is why in our maintenance checklist, the receiver is the first thing we are checking, because it will give us a very nice idea of what we should do, right? We need to go to, right? If it is work, do we need to go here? If the lock light is on, and I'm not receiving data, the problem should be here. If the lock light is off, the problem should be here. So you have all this information and the recordings that will help you during the maintenance. And just a final comment, if you have done everything, and made all the verifications, and everything seems to be fine. The receiver is working, fast client is on, but you're not receiving the files. Reboot your receiver, right? Here. Here. Reboot. Reboot your receiver and restart fast. Sometimes it works, right? And that's the objective of this presentation. So the idea is that you understand the basic key parameters that you need to check, how to check the basic specs of your workstations and visualize data. And finally, with the maintenance checklist, that you understand some of the parameters that you need to check in the future, okay? Because in the case of a possible problem, your station can resume the ingestion as soon as possible, okay? And in our next presentation, we are going to learn how to use a great software to develop our scripts. Let's move to Python now, okay? And let me see if you have any questions. And I have a couple of questions here. How regular should we do this? You know, this example here, it's for you to do when you stop receiving data. And based on the flow chart and then information you get here, you'll have a very good idea of what is happening. But if you do not have any problems, you can do that every 3 months, for example. So your technical staff are always checking and know how to check these parameters as fast as possible, okay? And how do you reduce the storage space, decrease the percentages? Here. Now that's a good question because you may easily add scripts to run in the background as a Chrome task, for example, to monitor your station and delete files that are, for example, older than X days, older than 3 days, older than 4 days, etc. But I really suggest that you study in your workstation how EEC is doing that, because each vendor does it in a different way. And us in our station in Brazil, we do it in a different way. So I suggest that you take a look at the Chrome tasks you have in your Linux machines and see how they are doing that. They are probably have a routine there saying, hey, I want to delete files that are older than a week or 2 weeks, and you can change that. So, uh, so you can check and reduce the usage, right? Okay, and if you do not understand Linux, we can discuss later and exchange emails, and I can share with you some procedures that you may take a look and learn how you may check this and change these parameters. Okay, all right. So that's the idea. You have your workstation working. You have softwares that are able to visualize the data, and you may use Python as well, right? You have everything you need to start doing interesting things. Now let's see how we can do some interesting things, learning what I'm going to show you in the next presentation. Just a moment. Here, Introduction to Visual Studio Code. Okay. In this presentation, we are going to see that there are other tools for creating and testing our Python scripts, right? And we will introduce a software called Visual Studio Code. And this is one of the most used software for development by the community in general. Now that we know the basics of Python and the possibilities that we have to process the products available in GeoNetcast Americas and other data reception mechanisms, right, like Amazon. In our homework notebooks, we are downloading data from Amazon. And we have already processed GOES-R and NWP data. The idea now in this presentation is that you learn how to increase your productivity, right, when developing your scripts. And I know that some of you were able to run scripts locally. I know that Eugene was able to do that. I know that Wayne, Chevron, and some others. I can't remember the name now, but if you have managed it, please send an OK in the chat window. Hey, I have managed it. But some of you have managed it, okay? And this presentation is especially useful for those of you who are already familiar with running scripts locally, as we have done today in our homeworks by, to process those images, those ash and dust RGBs locally, right? And you have this procedure. If you were not able to do that yet, we have seen the procedure is available on Moodle, right? If you open Moodle, here, this is the procedure that you may access. Processing GOES-R imagery with Python locally. And you have all the steps you need to process Python products in your machines, right? Everything you need. Okay. But if you are not familiar yet, there's no problem. And the idea here is that you understand the benefits of using what is called an integrated development environment, as we are going to see, okay? And the screenshots you're going to see, it may look a little bit intimidating, but the important thing is that you understand the benefits of using a software like this. So in the future, when you are more familiar with programming, or when your staff, your technical staff, is more familiar with programming, they may try it, or you may try it, okay? We are going to review how to run scripts locally. And we will see how to install and configure Visual Studio Codes. If you are able to run your scripts locally, you may follow the same steps as I'm going to do here now, okay? If, for example, Wayne, I know that you are using Conda and processing images, as we have seen in your plots. Okay, as we have seen here you have processed disk with Python locally, and this one too, right? So I know that Wayne will be able to follow this procedure. But if you are not able to do it now, you have all the recordings and the slides to try it later. And in the end, you check some extra features and benefits of using a solution like this one, okay? And in that procedure, as we have seen in the Python introduction in the first day, in order to run Python scripts locally, that is in your computers, you need basically these 5 items, right? First, Python, which is our programming language. Second, a package manager that will install the libraries we need to use. And third, a so-called virtual environment manager, right? To create the environments where our Python libraries will be installed, okay? And for these 3 items here, we can use a tool called Conda. And when you install Conda, you have in your machines these 3 tools, okay? That is why in the morning, I have used the Conda command. I have used the Conda command called Conda activate workshop, because in this procedure, I have created a virtual environment called workshop. And if I use the command conda list, you see all the libraries I have installed in this environment. Like, for example, netcdf4, matpy, matplotlib, and many others, hdf, gdol, etc. Okay. But you also need an editor to write your code, and that's the goal of this presentation, right? You have more simple options or more advanced interfaces, right? And you have many options. Notepad++, Visual Studio Code, PyCharm, Spider, etc., 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 right? And in the procedure, and until now, right, we have used Notepad++, which is this editor here. In the morning, I have used this editor to paste my script called script ash, and we have created that nice composite, right? Okay, but we have more sophisticated options, right? And you may ask, hey, why have we started with this simple option? Why haven't we used this one since the beginning? And the answer is that in the past, when we tried to use more sophisticated tools during the trainings, we noticed that the questions are more related than the software itself than the scripts. So to avoid these problems with the interface, we started using this simple option like Notepad++, okay? However, I know some of you are already developing images for your Met services, as we saw today, when you uploaded an image developed by Wayne. And maybe using a more advanced tool could help, right? And from these many options we have, Visual Studio Code is based on what I see here with my colleagues and by the community in general. It's one of the most used options, right? Professional programmers use this option here, right? It's one of the options they may use, right? Finally, we need data. We need sample data. And as we have seen in the reference slides earlier, there are many options, many data access options for you. And in the tutorial available in the blog, you see how to install Conda how to create an environment called workshop, how to install the Python libraries in this environment, and how to activate this environment, just as I have done 3 minutes ago, right? And we also learned how to download samples from the cloud to run our scripts. So in a summary, we installed Conda, right? In this case, mini Conda, which is a lightweight version of Conda. We create a virtual environment called Workshop, right? We installed Notepad++. We download sample imagery, or we can use the samples you have in your GeoNetCast Americas stations, which are the same. And we run our scripts, right? Here's an example of how we are running scripts with a simple editor like Notepad++. And here we have the first script, right? We have seen in this training in the first day, script number 1, use it to create a very basic plot with an ABI image, right? 8 lines of code, right? And during our demonstrations, we have seen that we needed to open a terminal. We need to activate our environment, as I have done right now, some minutes ago. I needed to enter my working directory, C, VLab, Python, etc. And I need to insert the Python name, the Python command, and the name of my script to run script number 1, for example, right? In the many demonstrations we've seen during the training, including today to demonstrate the RGBs, I always needed to repeat these steps, right? And after running these scripts, another window is opened with my plot. So in the end, I'm using multiple interfaces, as you're seeing here. They are not integrated, right? Let's make a demonstration again, okay? So here I have my terminal. Let me close it and open it again, right? Here I have my prompt, right? And here on this folder at C, VLab in my case, okay? Python goes, I have my script number 1, for example, right? So I activate my environment, conda activate workshop. I move to my working folder, C, VLab, Python, goes, sorry, and I run my script, Python script 1, the first script we have seen in day number 1. And here it is. Here's the result, right? So this is how we were doing until now. However, we can have everything in a single interface, as this, as you're seeing here, right? And this is one of the benefits of using an integrated development environment, like Visual Studio Code, for example. So we have everything and much more, as we're going to see, in a single interface, okay? So in this example, we have the File Explorer on the left, our script in the middle, the terminal below, right? And our output at the right side of the same interface. And as we are going to see, after configuring the software for the first time, you just need to click at the play button here, or use our shortcut to run your scripts with your environment. There is no need to manually activating the workshop environment, going to our folder and using commands to run scripts. And that makes things much easier and much faster. In fact, the definition of IDE, right, or an integrated development environment, is that it is a software application that helps programmers develop software more efficiently, okay? And also to increase the developer's productivity by combining capabilities like these ones we are seeing here, such as editing, building, testing in an easy to use solution, right? Okay, we already know the benefits, right? Now let's see how we can download and install Visual Studio Code, right? You may access this link here, and I'm going to send it in the chat, right? codevisualstudio.com. Right? And in the upper right, you just click at download. And you have to select your operating system. And here in this laptop, I'm using Windows, right? And you may click at Windows, and the installer will be downloaded to your computer. Okay? All right. Here, you just have to select your operating system and install it. And the installation is very straightforward, right? You just need to click next, 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 and finish, right? Okay. And when you run it for the first time, you will see a blank interface like this, right? And if you do not configure it, just a moment. Here's the file being downloaded, right? This is the installer, and it has 88 megabytes. It's not huge, it's small, okay? So you may just click it a couple of times and it will open the installer, as you're seeing here. License agreement, etc. It's very easy to install, okay? But I have already installed it, so I'm going to quit, okay? When you run it for the first time, you see a blank interface like this. And if you do not configure it, it looks like a very simple editor, like Notepad++, for example, right? However, as we are going to see, you may install the so-called extensions. And these extensions is one of the things that makes it very powerful. Also, it doesn't come ready to run Python by default. So you need to install the Python extension, right? And one of the nice things of interfaces like this is that you may use it with many programming languages, as we are going to see in the end. And you just need to install the extensions you need that allows you to work with that particular language, like Python, for example, okay? And when the installation is finished, you see an icon in your desktop, just like as I have here, Visual Studio Code, okay? All right. And to install an extension, you just need to click on the left toolbar here in these little blocks, right? On the search bar, you just search for Python and click install. Okay, so here in Visual Studio Code, supposing I'm opening for the first time, right? And I do not have the Python extension installed. I just need to click here, extensions, and search for Python. Here you have Python extension. I do not have the install button here because I have already installed it. Okay, all right. Let me go back to the slide. Here, right? Okay, now you have installed Python at this point, right? But you need to tell Python extension where is your conda, right? So Visual Studio is able to work with Python in your conda environment, right? We need to tell Visual Studio Code where we have our conda installation, where we have our workshop here, our workshop environment, as we have installed it in the procedure available in Moodle. Remember, we needed to do the same steps over and over again to activate our workshop in the prompt, right? In this example, we are just tell Visual Studio once, and after that, it will do it automatically. And to configure where your conda installation is and where your workshop environment is, you need to go to File, Preferences, Settings, Extensions, Python, right? And in the Conda path, you just need to insert your Conda installation where you have it. And in the default interpreter path, you just need to add insert where your workshop environment or any environment you want where it is, right? Let me demonstrate. I have Visual Studio Code open here. So if you go to File, Preferences, Settings, and search for extensions, Python, here you have, where is your Conda installation? And what is the environment you would like Visual Studio to use, right? And in my machine, it is on C users, D Souza, Mini Conda, Conda Bin. And my workshop environment is in D users, D Souza, Mini Conda, AMS, workshop, Python, executable, okay? All right. Also, I need to tell Visual Studio Code which is my working folder. And that's very easy, right? For goals, for example, for our first examples, I have my script at C VLab Python, C VLab Python goals, right? But you may use and open any folder you want. You just need to click in, right here, Explorer on the left toolbar and open folder and select your folder. Let's see. Here, Explorer, open folder. And I will open my C VLab Python goals, select folder. And here, right, you see all your files listed in the left part of the interface. Now it's much easier to find your files. Also, to open your scripts, you just need to click, and that's it. It will open in a new tab here. And you also may create a new script if you want, right? And this is the basic configuration. And if you click at the play button, right, the script you run using your environment and libraries. For example, if I click here, script 1 or script 2, let's see script 1. This is my script number 1, okay? And if I click at the play button, it is already processing my file with the environment I want. And here's the result. Much faster than opening the prompt, activating the environment, and looking for my files, looking for my working folder, etc. Okay? All right, that's the first benefit of using an IDE. I would like to make it better, right? And another thing I could do is, if needed, I want to be able to run Conda commands directly in the terminal available in this software, right? So I will change my default terminal to the Windows command prompt in this case, right? And to do that, you need to go to View. I'm going a little bit fast here, but you have all these recordings, all the procedures, so you can do it later, right? If you click at View, Command Palette, and search for Terminal, select Default Profile, you will be able to select your command prompt here, right? Let's go to our Visual Studio Code. If you go to View, Command Palette, and search for Terminal, select Default Profile, and click here, you will be able, oh, hey, do you want to use the command prompt, the PowerShell, etc.? I would like to use the command prompt. And with that, I will have my terminal here. Instead of having another window like this one here, I have it in my interface. So I can, for example, see the variables I have on the list directly in my environment. Okay, that's another benefit. Let me return to my presentation. Okay. As I have showed, if you click at the play button in the upper right corner, the selected Python script, script 1 in this case, right, will be executed. With the default code environment, which is Workshop in our case, right? And when you click the play button, you see the workshop being activated, right? And the script will run much, much faster. And here you have the result. The plot will appear, right? So that's the basic configuration of Visual Studio Code. Now let's see some extra configuration to make it a little bit better, right? And the first extra configuration I use is configuring a shortcut, a keyboard shortcut to run Python scripts with a shortcut. Because by default, you need to click on the play button, right? But if you want to use a shortcut, you may click this gear in the left toolbar, right? Select keyboard shortcuts and search for run Python file in the terminal, right? And then you just select the keys you would like to assign as a shortcut, right? So here, right? Keyboard shortcuts here, run Python file in terminal. And here I have assigned Ctrl+R, but you may use anything you want. So when I'm here, hey, I'm editing my script, and I do not want a grays palette. I want a jet palette, jet. Ctrl+R, that's it. My script is being run, executed. And I didn't even need to play here, to click here, right? And here's the result. Much faster, okay? All right, let's continue exploring it. Another extra configuration is, and this is a very important thing, is enabling Visual Studio Code to read files that are available in the same folder as the script. Because by default, you need to specify the full path where a given file is located. But if you want to put a file in the same folder of your script and just insert the file name as we have been doing until now, you have to configure Visual Studio Code to do that. So you just need to click at the gear icon again, settings, Python terminal execute file in dir, and check this option, right? Gear icon, settings, search for Python terminal execute file in dir, and check this option. With this, you can only specify the name of the file if the file is available in the same folder. Okay. Another thing I like to do is changing the editor color scheme. And personally, I don't like the default color scheme of the editor called the dark plus, right? And if you want to change the color scheme, you just need to go to File, Preferences, Theme, Color Theme, and select your preferred theme, right? Let's see. File, Preferences, Theme, Color Theme. You have a light configuration, right? Or you have many other options, themes, color theme. This is the default, right? But I personally like this one, themes, color themes, dark Visual Studio. I prefer working with this one, okay? But you may select any theme you want, right? Any theme you want, okay? So that's another step. Okay. And another very, very nice thing we can do is installing other extensions that would make your lives much easier. And here I'm suggesting to install the H5 Web extension. And this extension allows you to visualize NetCDF files or HDF files directly in Visual Studio Code. Not only visualize them, but explore the data sets. Okay, just as we have been doing with Panoply, for example. And to install a new extension, you just need to access the extensions menu, this icon with the little blocks, the left toolbar, and search for H5 Web, right? Extensions, H5 Web. And here it is. And I have already installed it here, okay? And with this extension, here's the nice thing. After the installation, in the Visual Studio Code Explorer, you just need to click on a NetCDF file, for example, and the file will be visualized in a new tab outside the interface. So in this example, I have just clicked in a NetCDF file for goals, right? And here it is, being visualized directly in the interface. And it's not just visualization, but I can even inspect the data sets, the attributes I want, instead of displaying the data set. And in this example, I'm checking the information about the goals are projection directly in VS Code, right? And more than that, you can also make some basic changes to the visualization, like changing the color scale, changing the minimums and the maximums, and much more, right? So if I go to my Explorer and click here, band 30, here you have, right? Another tab appeared automatically, right? And I can click here, the CMI variable, and it will be displayed. Here you have the number of rows and columns, 5,424, right? If you move the mouse cursor over the image, you see the pixel values, right? You can also change the color map being used, for example, from rainbow to let me see, turbo, for example. And here it is, okay? So as you see, and you can explore the values of the pixels. Of course, here I'm seeing, here you have values of the pixels, okay? So as you see, we are basically using the functionalities available in Panoply, but directly in Visual Studio Code, right? It's much faster this way, and as we said, an IDE increases the productivity, right? And here's another example extension called the GeoData Viewer extension. And that allows Visual Studio Code to explore geodata, like shape files, for example, which is a very nice addition, because when you are trying to use new shape files, you don't need a GIS to open it and study it. You can do that directly in VS Code, right? Here, for example. We don't have a shape file here, but we'll do that in the next session, okay? Another thing we can do to make things faster is seeing the output in the same window, like in this example. We are seeing the plot in the same interface instead of seeing in a separate window. And to do that, we just need to click in this arrow besides the play button and choose a run current file and interactive window, right? Okay. Oh, and before that, you need to install this library in your Conda environment, the interactive Python kernel. Okay. Let me demonstrate. If I go to my script again and click here and run current file in interactive window, it will show my plot directly in the interface. And when you run for the first time, it takes some seconds, but in the second run, it is much faster, okay? Here you have, okay? So you have everything in a single interface. Your files, your script, the output, the terminal, everything in a single interface. Another thing you can do is opening multiple scripts in the same window, like in this example. And to do that, you just need to click on this icon here in the upper toolbar, for example, like this. Let me close this window. You can open, for example, script number 1 here and script number 2 here. For supposing that you are, studying the scripts for the first time and you would like to compare the commands you have added here in comparison to the other, you can do that, right? And this could be very useful because you may quick check comments from another scripts and use them as a reference. And with all of that, we have reached our goal, an integrated development environment. It is a software application that helps programmers develop software code efficiently, increases the productivity, and it combines capabilities, right? The final information that I would like to mention is that with Visual Studio Code, it's very easy to create the so-called Jupyter notebooks. And Jupyter notebooks are basically Google Colab running offline in your computers, okay? So Google Jupyter is an application for creating and sharing your scripts, documents, texts, images, instructions, and much more. And Jupyter Notebooks is very popular. It is used by universities. It's even used for trainings related to satellites. Many trainings organized by NOAA and UMetSat, they use Jupyter Notebooks. And you may easily create one and visualize one Jupyter Notebook with Visual Studio Code. You just need to click at File, New File, right? And select Jupyter Notebook. And you will create a file with the IPYNB extension. Just like the extension that we have here in our, sorry, no, it's not this one. Look at the extension we have here in our Google Colab, IPIYNB. It's the same extension, right? You can even download your Colab notebook and open it with Visual Studio Code, right? And run your scripts locally. So you may, for example, develop something that you not consume your computer resources in Google Colab. And when you finish it, you download it and run it locally, right? And when running a Jupyter notebook for the first time, you just need to choose the content environment you want to use. In our case, workshop, okay? And here you have an example. And as you may see, you may create text cells and code cells, just like we do in Google Colab. Using the libraries we have installed in our computers, right? Let's make a quick demonstration. Here, File, New File, Jupyter Notebook. Let me close this tab. And here you have your Jupyter Notebook. And I can create a markdown cell, which is a text cell. I can delete it. Or I may create a code cell and insert my code, right? Let's make a demonstration, for example, markdown. This is a text cell. Hello. I can put it on bold and I can make it a heading. Sorry. This is a text cell. Hello. But I can also use, create a code cell. A is equal to 1, B is equal to 2, and C is equal to A plus B. Print, this is Python code, print the value of C is, comma, C, and run it. It is connecting to my workshop, and here's the output. Value of C is 3. So, and I can even import my libraries. For example, import net CDF, CDF4, and let's check the version of this library. Net CDF4 get lib version and run it. Version 9.1 from February 24, 2023. So you see, you may create a Jupyter notebook for your courses, for your classes, and share these notebooks with your students, for example, right? Or if, we have created a script to manipulate a satellite imagery and we want to share with our colleagues with some instructions and images and graphs, etc. You may create a Jupyter notebooks and share with them, just like we have been doing with Conda. Okay. Okay, so with Visual Studio Code, you have everything you need to start creating Python scripts locally in your computers. And you have a file explorer, editor, terminal, output, and many other features in a single interface, right? And one final comment is that one of the things I like the most is that about this interface, of course, it is free, it is lightweight, and you can use it with any other languages you want. Like, for example, C, Fortran, R, MATLAB, C#, Java, and many others, right? So you may use Visual Studio Code to develop your web pages, for example, right? Eugene, you are developing a web page with Django, right? You may use Visual Studio Code. I don't know if you are using it now, but you can use it easily, okay? You can also use Visual Studio Code for many applications, satellite data processing, web development, and much more. And personally, I also use it to work with electronic circuits and program my circuit boards. I just need to install my right extensions. So the possibilities are many, right? And that's the idea of this presentation, right? So we have seen an alternative to our development using Visual Studio Code. We have seen how to install it, how to configure it, some extra options to increase the productivity. We have also seen some useful extensions, how to create Jupyter's notebooks. And you're going to hear a lot about Jupyter notebooks in the future, right? And also, this is one of the most used tools, most used by developers. So for example, here at NPay, my colleague Douglas, the lead developer of DSAT, right? He develops DSAT. This tool here, the only thing he uses to develop it, it's Visual Studio Code, like you have just learned, right? Okay. Renato, my boss, he also uses this interface. Our colleagues from El Salvador, they also use Visual Studio Code. So this is a very nice tool. And if you're going to work with development, and some of you are, this is the right software for you, okay? And this was my last presentation for today. And next Friday, we are going to learn how to create plots and animations using Visual Studio Code, for example. So let me make a quick demonstration, right? What we are going to do. In Moodle, you have a folder. Let me access Moodle here. This is my model. Let me access CI&MA's model. The end of day 4, you have this assignment, creating advanced plots and animations, right? Here. And the password is workshop. Workshop. And you may click here at download link, and you will download. Let me close this. Everything I have opened and Visual Studio Code, right? And you have this folder here. Animation, it's called animation. You will download a zip file called animation. And inside this animation folder, you have some folders, subfolders that I will explain the purpose in the next day. And if you click here at myAnimation.html, you have an animation right here. And this animation is from July 28, 2020. Let me stop it. Let me open this structure in Visual Studio Code, for example. Open folder, C, VLab, Python, animation, for example. Select folder. And in this script here, under scripts, script animation, you may configure it to show anything you want. So let me make just a quick example, right? So this is what I'm seeing now. Just a moment. This is what I'm seeing now by default, but I can change. For example, sorry, I can change in the script date. Let me insert another date, for example, for Hurricane Ian, 2022, 09, 27, 17 UTC, until 28 UTC, until September 28, right? And I can change to, for example, band 8, and run the script with Control R. I'm running the script here, right, with a new configuration. It is downloading the file, right, reprojecting the image, plotting the image, and it will generate the image for me. Plotting the image, just some more seconds. Updating the animation. If you open the animation again, here you have, right, Hurricane Ian. Because I have changed the script according to what I want to see, right? And it is generating images for other time steps. Okay, but let me stop it. I will stop it. And here, if you reload it, it has generated 2 images. Here, 1, 2. It was already animating it. Let me change it again to, for example, 22, 09, 19, 17 UTC until 20. And band number 4, for example, but I can enter any band and run it again. Activated the workshop, download the time and date, downloading file, reprojecting the image, plotting the image. Let's wait some seconds. And I'm running this in my notebook, right? I'm not running this in the cloud. I'm running it in my notebook. That is why it's taking some seconds. Okay, animation updated. If I look at, here you have Hurricane Fiona in this case, right? And you can change anything you want. For example, let me make a final adjustment before we close the day, right? 2019 09 01 12 UTC, right? September 1 12 UTC 2019 until September 2nd, right? Band 14, and I will change the region to -85 to -45 as the longitudes, and 10 to 35 as the latitudes. Okay, and let me save it and run it again. Downloading the image, downloading file, reprojecting the image, plotting the image. It will take some seconds. Updating the animation. If you open it, here you have Hurricane Dorian for a total new region, right? So in this exercise, I just would like you to try, and you may plot any event you want for any interval you want, was for the band you want, right? And you can, if you understand a little bit more about if you feel comfortable, you may change any aspect of this script, right? But in the last day, I'm going to explain how it works a little bit more. And here we already have some more images created, so we can animate it. Let me test. Here you have, right? I have 2 images only, but it is still processing. And if you look at the web pages from Slider, ESAT, Geosphere, they do not have a historical files or images. They have usually a month, right? And with this script, we are demonstrating how you can do that and visualize anything you want, at least from goals, at least from the ABI, okay? And you can also use this file here, this HTML, right? And which is this HTML structure inside this folder called HTML, and you have all the files here. You may implement these animations in your web pages, okay? All right, so you have everything you need. You have very powerful computers. You have learned the basics of Python, and we will learn next Friday some more new tricks, right? And it's already 12:28. Let's close.
Diego, to confirm, the next class is Friday, is Monday?
Monday. Yeah, the last day. Okay. And that's it for today. And today we have started with the training, learning how to create the dust, the ash, and the SO2 RGBs. And after that, we have seen that it's possible that your Met services become a data provider of the GeoNetcast America system in the future. And we have demonstrated how you may upload your data when you are approved to be a data provider. We have also reviewed the reference slides available in Moodle. We have remotely accessed the station from Grenada and checked the fast client, the workstation's specifications, the Proteus software, Showcast, and we have filled the maintenance checklist table, okay? And we have learned how to install and configure Visual Studio Code, which is a very nice software that will increase your productivity when working with Python, right? And we finish it with the assignment from the 4th day, and we will give you more details on the last day, right? And next Monday, in the last day of this training, You'll see the community activities, right? Like the GeoNetcast America's user group webinars, the WMO satellite data requirements group, and after we introduce Showcast, we will finish the training exploring more products that are available in the GeoNetcast broadcast. Just for you to have an idea, we have this presentation here, right? So we will explore many of the products available there, right? Sea surface temperatures, perceivable water, vegetation, hotspots, ocean color, cirrus advected layer perceptible water, rain rate, and much more using Panoply. Now that you know how to use that, as we have seen in the first day, and also using Python. So you will see the last script examples from the last Colab notebook that we have available in the Moodle page, and you can access your Jupyter notebooks, your Colab notebook for this exercise for the last day in Moodle. And you see that you have script examples for a variety of products from GeoNetcast Americas, right? And that's it. Thank you very much. And see you next Monday. Have a wonderful weekend. Thank you very much for the interactions today. And thank you, Wayne, for sharing your files for the test uploads. Thank you, Eugene, and the others for the questions and suggestions. All right. Thank you. Bye-bye.
Thank you, Diego. Everyone, remember to please log off so we have a shorter file and a shorter time period. And Diego, as usual, excellent presentations and excellent. I look forward to not only participating, doing the scripts, but other products that people are producing. Looking well.
Okay.
Have a great weekend.
Thank you, everyone. Have a great weekend. Bye-bye.
Bye.